and let's talk about this topic, quality of service. Now, quality of service, when you think of the word quality, you might be tempted to think of things like quality standards, like ISO 9000, or you might think of TQM, or you might think of quality control or quality management. It's not really that. Okay, so those forms of quality, what they are is they're about meeting a customer demand. When we do that, we say that we are delivering quality. We give them what they want. Quality of service is kind of related to that, but it's a little bit different. It's actually about prioritizing our customer demands, it's assigning a priority to it. So by almost by definition, quality of service means that some customers are not going to get what they want, um, because their demand is going to find a lower priority. And so that's what we mean so quality of service is a way of taking a limited resource and distributing it in a way that best suits the organization, or whoever's paying for it or whatever. So it's not equitable or fair or whatever you want to call it like that. It's not done that way. It's done in a way which best suits the organization. And so that is sort of represented. Well, I don't mean to sound like it's not fair. I mean, it's the organization distributes the resource in the way that best meets the needs of the organization. And in the long run, that means it would be fair, because the organization doesn't do that, then it won't stay in business, and then nobody is going to be sorted out, right? So what it is it's a way of basically rationing, I guess you'd say, a limited resource. And so that's supposed to be represented by this nice diagram here, which looks like a pipe with a bunch of stuff coming out of it. And you'll notice that the stuff is sort of separated into different sort of parcels or parts. And that represents the fact that in this one service that we have, which could be a networking service, but most likely this is a networking service, we have a lot of different types of data going down through that service. In fact, we might be doing voice over IP. That's what this means here, this real-time voice. And we actually have a way of separating each of the different channels, I guess you'd say, of different kinds of data that go through there, and then allocating to make sure that they get the amount of that bandwidth, which serves the organization. And so that can be represented by a diagram like this, where we see that, we should mention that, right? This is governed by the service level agreement. So by now you've heard of service level agreements a bit, I hope. The idea of a service level agreement, very important word in service level agreement, is level. It's not just a service agreement, it's a service level. And so that, I hope you can see the implication in that word, is that there can be different levels of service, depending on the priority, depending on the customer. And you would have come across that in the organizations which I think best sort of exhibit this, which is telecoms organizations, because they provide a service very much like a network. They're a network-based company, right? And they do provide service levels that are different for their customers, depending on the priority of that customer, usually depending on how much that customer paid for that monthly service. So, for example, they're selling to some people a HALID package with so much data and so much voice, and selling to other people something with more data or fast, or you got different fiber. We all have fiber coming into our house, but depending on how much you pay, you might have a different amount of downloads you can do and that kind of thing. So that would be a service levels that are differentiated depending on the different customers. And so that is governed by a service level agreement. You might say, oh, well, I don't remember signing a service level agreement. Well, and in fact, you would have when you went to Orito or Vodafone, and you got your service from them, there would have been an agreement that you would have had to sign. You probably didn't read it because everybody just accepts it because they know everybody else has got an agreement like that. And so, yeah, I just want it. So yeah, just charge me the 500 reals a month or whatever, and I will take it. And, sometimes we look into it really closely and sometimes we don't. Okay, so now this is represented by this diagram here. I like diagrams. And what we see here is two different service channels or streams of data that are approaching a router. And we notice that on the other side, which is represents the actual communications link coming out from that router, only only one of those data streams is actually passed on to the network. And so that actually represents the fact that there's some application program running on that router, which is differentiating the different streams of data, and one is allowing to go through and the other is not. This could be described as a quality of service, which is being applied on that router. And so that router is prioritizing a particular application and lowering the priority of another. Now you might say, oh, well, why would they lower the priority of the guy on the computer? Well, probably that represents maybe computer gaming or something, right? And this represents our normal voice over IP or normal telephone um, efforts. So we have a number of ways of measuring. That's these things here in this dot points represent things that we can do to measure to make sure that our customers are getting that service level that has been agreed to them, that's been contracted to them. And so we put these measures into the service level agreement, and then we have some tools so that we measure them over time in terms of what they're getting over the network. This diagram here represents the fact that the actual usage of the bandwidth in the network is not constant, that it changes from time to time, and sometimes that there seems to be an underutilization, but at other times we find that the utilization almost takes up the available capacity. Or the total capacity, right? So the available capacity is actually that capacity that's between what's being utilized and what the total capacity is. But if the utilized capacity gets up pretty close to the available capacity, we're going to get to a point where we have a blockage, I guess you would say, or that the data is not going through at the speed that is required to get those to make those applications at the, well, as it says, at the fixed bit rate, which has been contracted. And so some of the things that we can measure, one of them is jitter. So what we're measuring here is negative impacts of too much utilization on that network. And so jitter will happen when there is too many packets. The packets cannot be supported by the network. And what jitter is tried to be represented in this diagram, which is that even though we set out packets onto the network, we loaded those packets onto the network in a very sort of regular fashion, that the time distance between them was regularized, was the same. What actually happened when they arrive at their destination is that some of them seem to be paused, or they take longer than others to arrive. And so we refer to that as jitter, and it is a problem because the receiving station on the other end is expecting to receive this packet at this point here, and it doesn't arrive, and so that can cause some issues depending on how long that time is, that pause between. You could even have a situation where the node that didn't receive it asks for a resend of the packet. So we have this term which we use to, this is a positive term. Jitter was a negative term. So we have this positive term throughput, which will include in the service level agreement. And the idea of throughput is a measure of how much successful packets, what is the level of agreed upon or guaranteed minimum or minimum packets that will be or maximum throughput. Yeah, I guess you could have a maximum and a minimum could be agreed upon by between the people in the network and their customers. So if you had agreed upon a throughput level, and as I said, throughput is going to be the successful packets over a particular time. And it's very important that we focus on that word successful, because we could load a whole lot of packets up there and say they could go halfway there. That is not going to be measured as part of the throughput. In order to be measured as part of the throughput, those packets are going to have to successfully arrive at the other end. Again, we've got a diagram there that represents the actual utilization of the network compared to the capability to the total capacity of the network. We can see that you can get to a point where the utilization is very high, and then we have a real big problem at this point, right? Because we've got two things going on. One, the packets. The packets have the actual volume of packets on the network at that time is raised high. But on the other hand, the actual capacity of the network is reduced because of, well, things like data loss. That is, that packets that have been dropped off, they've been put onto the network and then dropped off, and so they had to be resent. Data jitter, which is sort of related to that. So latency is just a measure of the total time between sending and receiving. But we have these issues, and RTT there, we have these issues there that are negative for our customer and are going to reduce the throughput at that point. And so successful passage of the or delivery of the packets from one end of the network to from sending to receiving stations on the network. Now, I know you've be familiar with this measure that we have, which is in bits per second. That we can use that as a measure for our system throughput. Bits per second, bearing in mind that a bit is like the smallest sort of unit of computer information. And in actual fact, we can't really do much with a bit, except maybe Boolean. We tend to use bytes, and so your byte is going to be at least 8 bits. And so though we measure it in bits, we're going to have bytes, and then those bytes will be formed together in packets, and packets have some sort of headers on them and that type of thing to indicate the protocol that is used to send that packet. And so there's the actual data is not the full amount of bits that are sent, and I'm sure you're familiar with that. But still, we measure bits per second. Now, in this diagram, what is trying to be shown there is this concept of latency. Latency being the time that it is required from the time that you send the packets out onto the network to the time that they're received. And latency, as indicated in the notes on the side here with this diagram, latency varies depending on the medium that's used. So for example, if you're using fiber optics, we're having latency there that is mentioned there of 4.9 microseconds per kilometer. Okay, so that's like, now you know all of these things, light, electricity, they're basically sort of limited. The fastest that we know things can go is like the speed of light. And all our media have some resistance in them. And so the speeds are actually less than the speed of light. But electrical current with electrons rather than photons, they're actually, the resistance there is going to be a little greater. And so that's going to be a little bit slower. Now here we say the latency of a satellite is going to be in seconds. Yeah, okay. And we know that. And I think that part of that is because it's just so far, right? So how does it work with a satellite? You have a satellite transmitter. There's a big dish thing. As far as I know, there's one out there on the road between Shahania and Zubara, and there's another one down there on south of the bases, the military bases there on off Shamal Road, not Shamal Road. That's the other one, Salwa Road. There's some there's some large dishes there that communicate uh, with the satellite, with some satellite, telecommunication satellite. Now, those dishes are both transmitters and receivers, as far as I know. So they're going to send a message up to a satellite, and then that satellite may communicate with another satellite, and then send that message down to another receiving station on the other side of the world, and then it goes into a network. So that's going to take some time, and so that's why it talks about seconds. But fiber optics taken some time too, right? It's 4.9 microseconds per kilometer, but usually we're communicating for more than a kilometer, so we're going to have to multiply that number by however many kilometers it is. So it's sort of distance and time thing, right? We are limited because there are these particles, waves. I'm not going to get into sort of quantum mechanic theory here, but it's particles or waves, and it is limited in speed by the speed of light, some number slightly less than that. Now there is this concept. So aside from our speed being limited by just physical reality, we also end up losing some of the data that's actually put onto the network. So packets are put onto the network, and some of those packets segments are lost, and so that causes a problem, and they might need to be that has to be mitigated somehow. So we put in some special equipment with monitor and measure. For example, here's equipment that people have put in there to check that. Here we've got this special software that protects particular segments. And so, yeah, there's going to be some mitigation, and that's going to be an overhead on your network. So packet loss is bad. And when we have channel congestion, we are likely to get some packet lost. Some packets are going to be rejected if they're corrupted or whatever. If our hardware is faulty, we could lose some. And our routers have protocols on them, some of which may cause some problems with us getting those packets through. So, for example, in our dynamic source routing, DSR, that may cause some packets to be rejected and lost. I've already sort of mentioned this point about the bandwidth. So just going to mention it here with a nice diagram. The diagram, we use pipes quite often to represent this concept of bandwidth. This is abstract, of course. We don't have sort of pipes, and I know if you sort of studied your fiber optics and things like that, you would have learned that the thinner the fiber optic, it's not a wire, is it? Fiber optic thread, whatever you want to call it, fiber. The thinner the fiber, the higher the capacity. Isn't that interesting? So I mean, we don't have these great thick cables, but you do have multiple fibers. But so this doesn't sort of represent something physical, but what it represents is a abstract sort of way of showing what's the difference between a fat pipe and a thin pipe in terms of bandwidth. So we talk about fat pipes and thin pipes, basically a fat pipe being one that has a bigger bandwidth. And what we see here is that we have a certain amount of the latency, all right, is going to be taken up with things that are not dependent on the bandwidth. And so that is sort of fixed. We got the time that it takes for all of the getting the protocols organized, sending out the packets, etc. That is fixed. But the actual passing down the pipe, that's going to depend on the fatness of the pipe, I guess you'd say. So we measure that in our in terms of gigabits per second, that type of thing. And so the diagram here is meant to represent, well, suppose you put a large image onto the network, and the latency on two different networks, one which has a bigger bandwidth than the other. it's going to be the same, but the actual image will download faster on the one with the higher capacity of bandwidth. A bunch of ways here listed in dot form that we can improve the efficiency and the effectiveness of our networks. So this bunch of, mostly you'll see here that it's intelligent use of software and or hardware to increase the actual throughput. So, and this, the point that I want to make here is, without actually making huge changes to the infrastructure itself of the cables and stuff like that, there have been obviously improvements in the medium, the cables, and I mean the greatest one was the fiber, wasn't it? But so that's improving too. But even with the existing fiber that we have out there, we see going forward greater bandwidth out of that same infrastructure by using better hardware nodes, but also using new software protocols, etc., which are able to get higher band bit rates coming through the same fiber. And so these are some of the ways that happens. Basically using intelligent techniques to get a better result at the other end. So let's have a look at some of those. So one of them is this idea of deduplication. The idea being that in any huge sort of stream of data that we might put onto a network, there's going to be a lot of redundant or repeated elements within that data stream. And so what can happen with deduplication is, what you're going to do is you're going to take any of those elements that are repeated many times. So we see this red one here, it's repeated many times. And in the stream that actually comes and is received at the other end, only one of those. And, we can do that and then sort of have some kind of index with it to represent the ones that we didn't bring along. Just like, okay, so like the word the was came through in that data stream like 100 times. This is the word the, and here's an index of all the places where it could be. So that way we have a lot less data has to come through to get the same message. Another thing that we can do is we can do this thing called compression. And you probably have seen that. We try to make things smaller without losing them. And actually, even JPEG, that is the pixels in your JPEG files have been compressed to give that result. But we can compress them further with zip and RAR, etc. And so what they're doing is that we know that we have headers on all of our packets, and we can compress those headers. And by doing that, we can actually increase our throughput. See the throughput here with the compressed header, and therefore reduce our delay, which is part of the latency that is measured and is something that we want to try and reduce. And so that's one thing that we can do. Other things that we can do, and as I said, a lot of these things that are increasing the throughput is just really very intelligent sort of tweaking of the protocols that we're using. So you'd be familiar with the TCP and the UDP protocols. The TCP protocol being the one which is connection oriented. And so that protocol actually, because it requires an acknowledgement, so it's going to be a little bit, you might say, slower, and we use it carefully. There's some places where we just go ahead and use the UDP protocol because we're not too worried about the data integrity being exact. So like if you're streaming video, you got a lot of data coming down there, and you don't mind if you lose a few packets here and there. As long as you can get that coming through quickly, it'll be all right. On the other hand, if we're doing banking application, we don't want to lose any packets. We don't want to lose even one, because that's money. So there's some cases where we do need to use TCP, and it's a little bit little bit slower because there's a little bit more overhead on it. But there's some tweaks that we can do on that to also increase that the throughput on that, and those are sort of mentioned there. Okay, and so we can work by tweaking the Windows size, which is going to sort of average things out a little bit better. Co-location strategies, local WAN optimizers, etc. So there's tweaks that we can do with the TCP. The idea of using a proxy cache server, I'm sure you might be familiar with that. This was kind of nice, but has a bit of a downside, which I'll just mention in a second. So the idea is that we keep on accessing. So this web server, all these clients are accessing this web server all the time. And what we notice is that they're all accessing the same one all the time. So we can make a copy of what's on that web server and keep it on this cache server in our local, right? And then the client can access the cache, and only from time to time do we need to access the internet. So they don't need to access that web server directly. They can just access the cache server, and that'll usually give them what they need. That'd certainly be okay if you were just sort of accessing a static website, like an information news website or something like that. That probably work pretty good. But if you're going to be using a dynamic website where people fill out forms and stuff like that, then this might not work so well. Another one where it won't work so well is supposing you're a developer and you're developing a website on your web server there, and what happens is the local proxy server just by default is keeping a cache of that, and you do some changes to it on your computer here, and then you upload it using FileZilla or whatever, and then you go to check it. No, nothing's changed. Well, that's because you're not actually looking at your website. You're looking at the cache, which hasn't changed, and so you have to maybe refresh the cache, maybe turn it off and then turn it back on again. Another thing that we have that can speed things up, I guess what we're trying to do is get our throughput as big as possible. And we got I got 7 minutes left. All right, because I do need to sort of let me stop when we get to 5 minutes or something. We'll take a roll. So stay on until then, because I'll mark the roll again, and maybe we can just have a brief discussion then. So we got 7 minutes. Let's see how we go. So forward error correction. What we're doing here is regular intervals. We add an extra packet. Okay, so that's what it means by every n packets. At regular intervals, we add a packet, which can be used sort of roll back and get our and get any packets that may have been lost. And so it's a way of reducing the distance that we have to go back, I suppose, to do resend data. So there's a lot less data that's going to be, or a lot less packets that are going to be resent. And the graph sort of shows the effectiveness of that. So what we see here is if we don't have any forward error correction over time and distance, we have quite a few packets needing to be resent. Okay, but if we are doing forward error correction, we find that we can put quite a few packets onto the system before we actually have to start doing resends. So it's pretty good throughout this part of the graph here, this bottom part of the graph. We're not having to put any resends, and so it's working very well. Now at very, very high throughputs, yeah, it's going to break down, right? But in this area here, it's doing really, really well up until a particular point. Okay, now the idea of protocol spoofing, what we're doing here is we have multiple protocols, so multiple different types of data packets that are being put onto our network. And what we do is kind of just roll them into one. And so that can actually reduce the congestion on the network, reduce what's being put out there. Traffic shaping, this is probably the granddaddy of the things that we want to talk about here. This is the one that we have tools that we can use for this, and we do use that. And let's talk about what it does. So We have two diagrams here which represent it pretty nicely, without and with shaping. So what our shaping is going to do is it's going to reserve a certain amount of the bandwidth for a particular application, and that'll be based on the priorities. And that's what I was talking about at the start. And you can refer back to that very first diagram that we had, which was the cover page kind of thing. And the diagram at the top kind of represents why there's a need for this. So suppose on our network, we had recreational users, they're watching YouTube videos or they're playing computer games. And then we have people using email, FTP, etc. Then we have our business critical applications. And what we see happening in a sort of free for all, wild, wild west situation is that the recreational use on the network can expand so much that it gets to the point where it's cramping and maybe forcing out business critical applications, email, etc. And so we don't want that to happen. So what we do is we just reserve a certain amount of that bandwidth that's only going to be used for business critical applications. And we reserve a certain amount for these others. And we don't just stop the recreational users, but we limit them quite a bit. And yeah, there's a number of tools that we can do for that. I don't know if you have come across this, but what I need to say here is the network capacities are growing quite fast, and also the priorities change. So what I mean by that is, like 4 or 5 years ago, I know that they were traffic shaping on our network here at the college to stop video and stop voice over IP. And that was because it was, this reason here, right? We wanted to keep the limited network available for our business critical applications. Well, now that's going to be changed a little bit, partly because video has become one of our business critical applications. Now, video, for example, Zoom, what we're using now, wouldn't be very good if the computer network here didn't allow Zoom communications. And how are we going to know if you're using Zoom for this or for playing computer games? I don't know, but so I don't think you're going to have Zoom is going to be blocked by the software. It won't be. There may be other video-based applications that are blocked, but I think that that's much less now. They've sort of built in a lot more capacity and also recognize the reality on the ground, which is that people are using the network for video, because it's just what we have to do in the modern age, right? In the ever since 1 year ago. Okay, so equalizing, another idea. This is another similar but very different idea. What's happened here is we do some analysis of the actual traffic, and we see a pattern. We see that we have a very big spike in the traffic, which is maybe even approaching or exceeding our capacity, and that spike is followed by dips. And so what we can do is run some kind of software that will basically cut off the top of those spikes, and then we can put the data that came from that top of that spike into the sort of the valley that is available with the lower there. Now that, as opposed to, we did two different approaches. We see the rate limiting shaper, which just cuts off the extra data, as opposed to rate equalizing scheduler, which is I hope that you'd see that would be preferable. So in this case, no data is lost, but the data may come a little later than it was sent. And so that's a way of sort of getting over a capacity sort of scrunch. We got 1 minute left. I got to stop. We'll come back to that in a minute. Let's stop and let me just check that. Oh, let me see, because I know it's going to stop. So let me make sure I've got, as best I can, list of who's here. Anybody got any questions or points that they want to mention? Chat, we got 1 minute left, less than 1 minute. So guys, have a nice day. We'll continue with this like tomorrow. We should finish it then. and then we spend the rest of our time sort of working on